Hi, Stephanie.
Good morning, Professor.
Good morning.
Hi, good morning.
Good morning. How are you guys doing?
Pretty good. How about yourself?
I'm doing okay. This is starting to feel normal.
I know, right?
How was the homework?
Oh, I thought it was pretty easy. It was fairly quick. I actually I had other stuff to work on throughout the week until I started mine Friday, but I had a good understanding of it, so
Oh, good.
easy for me.
Good. Giving it a couple more minutes to see. I have to admit people individually, and so I don't want to start talking and then not see someone waiting to join. Okay, I think I think we've got a stable number. I'll check and see if people join later and need to be admitted. Let me share a screen. Okay, so you guys see the lesson plan, the schedule?
Yes.
Okay. So hopefully you guys look through the slides And I was hoping people would try to do the Lewis structures on slide 29, just so that they get a sense of whether or not they're understanding it. Ooh, I think I need to let people in. Hold on. Yeah, there's a couple more coming. Okay, so how were the Lewis structures? You guys you can type whether type how it went. Was it easy? Was it hard? Was it so? Or you can speak also. I'm trying to find my chat window. Okay, so were the Lewis structures hard? Did you do them?
The Lewis structure seemed pretty well explained through the slides for me. I got a little confused when it came to like the double and the triple bonds.
Okay.
But it seemed pretty self-explanatory with the valence electrons.
So maybe what I'll do is I'll do one relatively simple one, and then one with double and triple bonds and resonance and other, and also greater than an octet. And then I thought, how about, have you guys gotten to the shape of molecules yet? Okay. Okay, so we have this homework is due Friday. Make sure you give yourself a chance to be able to learn the software associated with drawing molecules in Pearson. And we'll go over shapes. On Wednesday, I'll have the next chapter ready. That is, the chapter 11 is gases and gas laws. And so I'll be supplementing the slides that are posted with videos to help with explanation. Bring whatever questions you might have for chapter 10 in the homework on Wednesday. And I recommend reading through the first half of the chapter 11 slides. And then it came up quickly. Our next exam is going to be a week from Wednesday, and that's on that's on chapter 9, 10, and 11. So the electron configuration, periodic trends, Lewis structures and molecular shape, and then also the gas laws. I gotta let somebody in. Okay, more people coming. Okay, so for a simple Lewis structure, let me do a different screen share. Okay, so you all can see the notepad now?
Yes.
Yeah.
Good. Okay. Okay, let's do two Lewis structures. One is PBr3 and the other will be sulfate. Ooh. My camera seems to be, you guys see the notepad, but I think it's frozen.
Yeah, it's frozen.
Okay, let me relaunch. looked better. And then I gotta reshare it. Okay, now you see the molecules I drew?
Mm.
You see the notepad?
Yeah, now we can see it.
Yeah.
Okay, good. There's got to be at least one technological issue each time, right? Hopefully that's it for today. Okay, so let's do the Lewis structure of PBr3. Now remember the steps for determining the Lewis structure. Our first thing is you count the electrons in each atom and the valence in each molecule, the valence electrons. So how many does phosphorus have?
5.
Yeah, thank you. And we have 1 phosphorus. Then we have bromine, 3 of them. Bromine has 7. So that's 21 from bromine. That gives us a total of 26 electrons. Oh wow, this is really slow. One thing I'd like to point out is that I think I got people waiting to come in. Oh, there's Bill. Okay, I think I got everybody. Okay, if you add up your electrons and you get an odd number, double check, because it's very rare to have a stable molecule with an odd number of electrons. So this will almost always be even number. Wow, it's really, it's pretty slow, huh?
A bit.
Yeah. All right, so we have 26 electrons. I'm gonna put phosphorus in the middle. There's 2 things to consider. It's generally gonna be the least electronegative element, but sometimes that's not so easy to figure out. For us, it will almost always be the least abundant element that will be in the central atom. So I'm gonna establish a framework. I put phosphorus in the middle, and then bromine on 3 sides. Put in bonds between all of the atoms, and then I subtract that off from my electron total. So -6, that gives me 20 electrons left. And then according to the steps, the thing we do next is we fill in the outer octets. So each bromine has 2 electrons. It needs 8 to get an octet. So I'm going to give each one 6. Okay, 6 times 3 is 18. Now I have 2 electrons left. The next step in our process is to fill the inner atom octets, and that's phosphorus. Phosphorus has 6 electrons right now, 2, 4, 6. So I'm going to give it 2 more so that it has 8. And then I've used all the electrons and I have none left. You guys okay with that?
Yes.
Good morning, Professor.
Good morning, Bill. Okay, so
Always having problems getting in here. I'm here now. Okay.
yeah, it's a bit slow today. So a quality control on your Lewis structures is to check the formal charge. And I don't think this is covered in your book. The formal charge, there's a formal charge for each atom in the structure. And the way we calculate it is it's the number of valence electrons minus the number of bonds minus the number of unbonded electrons. So the formal charge of our phosphorus is going to be the number of valence electrons, that's 5, minus the number of bonds, 1, 2, 3, minus the number of unbonded electrons, that's 2. So it has a formal charge of 0. We want to have a formal charge of 0 as much as possible, and so that's good. all of our bromines have the same number of electrons, so we can calculate the formal charge for all of them at once. The formal charge, the number of valence electrons of bromine is 7 because it's in group 7A. It has 1 bond right here, and then it has 6 unbonded electrons, so it has a formal charge of 0. So this is a good Lewis structure. Do you guys have questions on this one? The next one's quite a bit more complicated. Holy cow.
I have one, Professor.
Okay.
And the reason I have this one, because the book gave 2 completely different Lewis structures for it. It was SO2.
SO2. Okay, let's see. Oh, it
And they
looks,
said, depending on what book you look at, it could be one way or it could be another way.
yeah. I think my camera froze again. Wait, there it is.
No, I'm having video problems too.
Yeah.
You're still up and running. It's kind of stop motion, but you're still moving.
Yeah,
It's like off by a couple of frames or something.
okay. Yeah, it's slow. But I'm still live. It has frozen. I think it completely froze once.
The audio was working perfectly though.
That's good. So you can hear me curse when it freezes next time. Okay, so let's do the Lewis structure for SO2. Count the number of electrons. Sulfur has 6. Oxygen has 6, but there are 2 of them. So that's going to give us a total of 18 electrons.
Right.
Okay, I'm going to put sulfur in the middle. It's less electronegative than oxygen, and there are more oxygens, and the oxygens on the outsides. And I'll put in bonds. So each bond has 2 electrons. That gives me 14. And I'm going to fill the outer octets first. 2, 3, 4, 5. So I use 12 to do that. Then I have 2 left over. Okay. So I have filled the outer octets of the oxygens, but sulfur, how many electrons does sulfur have?
6.
Yeah, that's not enough. It needs to have 8. But I've run out of electrons, right? I've used all 18 electrons.
How
So
come the sulfur has a pair of electrons and they're not like one on each side?
electrons generally go in pairs.
Okay.
Yeah. If you should really keep them as pairs. Unless there really is an unpaired electron, which you might see once, but generally we don't deal with those kinds of molecules. Okay, so if you run out of electrons and you have atoms without octets, then you need to borrow from one of the atoms to create the octet. So I'm going to take 2 electrons from this oxygen and I'm going to move them, make this so you can see it better, move them to create a double bond. So right now, this oxygen has 2, 4, 6, 8. My central sulfur has 2, 4, 6, 8. And this oxygen has, sorry. Been waiting for that call since Friday.
You sure you don't want to take it?
Yeah, hold on. My watch is still. Okay. Sorry about that. So, and this oxygen has an octet as well. Now, what I say is to assess the quality of your structure, calculate the formal charges. The formal charge of the oxygen that has the double bond, that's going to be 6 electrons from the valence, minus the number of bonds, that's 2, and then minus the number of unbonded electrons, that's 4. That gives us 0. The formal charge of the sulfur is 6 valence electrons minus the number of bonds, it's 3. And then the number of unbonded electrons, that gives us a +1. So it's not 0, which we ideally can have, but sometimes you can't always get all of your atoms to have 0. And the formal charge for the oxygen with a single bond is 6 minus the number of bonds, 1, minus the number of unbonded electrons, that's -1. So notice my formal charges add up to 0, and my molecule has a 0 charge, so that's okay. If there is a way to have these without a +1 and -1 formal charge, we would make that change, but I don't think that it's possible. So this is okay. But
Okay.
Question?
Okay, Professor. I did it another way also, and what I had sulfur in the middle with the two charges on top.
2
and I had
electrons on top, you mean?
2 electrons on top, and I had double bonds on both sides of the sulfur.
Oh, wait. You know what? I think we can do that. So, because this is sulfur and it's in the 3rd row. So let's see what happens if we do that. I'm going to draw that separately. So that would look like this. Correct?
Correct.
Okay. This actually might be okay. So the formal charges on both those oxygens is going to be 0 because it has a double bond and 2 unbonded pairs.
Right.
And the formal charge on that sulfur, if that's 0, this is a better structure. So, and this brings up an important point. So the number of valence electrons in sulfur is 6, minus the number of bonds, that's 4, minus the number of unbonded electrons, that's 2. So this actually is a better structure. Now, there's something that might bother you about that.
Something did bother me about that.
Why does it bother you?
Because I looked at this thing, and I think this problem showed up in Pearson. And the answer was your top one, and I put the bottom one in and got it wrong.
Oh, that's not good.
Pearson doesn't accept both.
Let me explain, okay? So, and I'd have to look specifically how they worded the question, but this sulfur here has an octet, 2, 4, 6, 8, right?
Right.
This sulfur has 10 electrons, 2, 4, 6, 8, 10.
Correct.
You can do that with sulfur because sulfur is in the 3rd row. And even though they're not filled, there's 3d orbitals.
Mm-hmm.
So elements that are in the 3rd row or lower can have more than an octet. It's called an expanded octet. If
Right.
that had been oxygen, we could not do that, or nitrogen or carbon. But you can do it with sulfur because it's in the 3rd row. Anything below that can have an octet, can have greater than an octet. And the way you check it is you calculate the formal charge. So this is a better structure than this.
It's so confusing, Professor.
But you got it right.
I know, but I didn't feel comfortable with this, because I didn't know you could do it both ways. I had both of them done, then I had to flip a coin as to which one I was going to call correct.
Well, you look at the formal charges, and I would say if I saw this structure versus this structure, there's only about a point difference between the two of them.
Right.
In terms of scoring. So.
Professor, I sort of have a question for the group, if I can present it.
Sure.
In that Pearson, there's a problem where you had a bracket around it after you made the Pearson structure, and you had two electrons on the outside of it left over. So I must have worked half a day trying to get that two negative on the side of that bracket where it should be. And I went all through Pearson, and I could not find out how to do that.
No, you use all the electrons in the structure. The 2- on the bracket just means that there's a charge on the species.
That's right. But I
How to
couldn't
put the bracket, like how to like put the sign in there.
Oh.
Like,
get that sign up there. I knew what the answer was, but I couldn't get Pearson to put that 2- up
do
there.
you know how to
because
put
that
the bracket in?
I got the bracket around the Pearson structure.
So at the bottom, there's a plus and minus sign. It almost looks like it's used to zoom in, but you click on the minus and then you hover over the bracket and click on the bracket, and then it'll add the minus sign in there. And then you can type in like a number if it's more than -1.
Let me try that. I worked all day on that trying to get that thing to work. I must
Yeah,
have
it's
clicked
in the
that,
bottom left-hand corner.
yeah, I clicked that structure down. I clicked that minus sign numerous times and tried to get it back up there. And I couldn't do it.
So you have to click the bracket after you click the minus sign.
Say that again.
You have to click the bracket after you click the minus sign.
Okay. After you click the minus sign first, then you click the bracket, correct?
Yeah, and then it'll pop up and it'll give you a little text box to put in like -2 or -1 or -3.
Okay. Do you click the bracket on the screen or the bracket little bracket icon?
The bracket on the screen, the one that you made.
Okay. Okay. Thank you for the help.
Thank you, Nessa.
Thank you for the help.
Okay, so we also have to think about the shape of molecules. If you look at PBr3, I'll redraw the Lewis structure. PBr3 has what we call 4 electron groups.
Right.
And an electron group is either a bond. It's the number of things. Oops. It's the number of things that are going to get spread out from the central atom. So our central atom is phosphorus, and there are bonds to 3 different atoms, and there's 1 unbonded pair. And valence shell electron pair repulsion theory says that electron pairs, whether or not they're to bonds or unbonded pairs, they repel each other, right? Because there's electrons in the bonds and there's electrons here. And so they're going to spread apart in space as far as possible. If you have CO2, the Lewis structure for CO2 is this. It has 2 electron groups. That means that this oxygen is coming out from the central atom, the carbon, and this oxygen is coming out from the central atom. And they're going to try to get as far apart in space as they can because the electrons in those bonds are repelling each other. And notice that a single bond counts the same as a double bond or a triple. Those are 1 electron group because they move together. The double bonds move together. So what is the angle that separates those 2 oxygens around the carbon?
180.
Yeah, and I used to, this is one of the lectures I like to do in class because you get a chance to try it yourself. So I've got a line here. Actually, I'm gonna bring my plate because it's gonna drip. I've got a line here, and if I'm trying to separate my toothpicks as far as possible away from each other, it makes a straight line. And that angle is 180 degrees. And in this case, my oxygens, which are on either side of the central atom, I'm already getting sticky. that shape is called linear. So this is 180 degrees, this is linear. If I have a molecule, and you guys, I posted a link to this table. This summarizes everything in the PowerPoint.
Can you show why water isn't linear?
Yeah, I'm gonna build up to that. Let me do one before that.
Okay.
Okay, so before I get to that group. So BF3 and has 3 electron groups. The Lewis structure looks like this. Each fluorine has 6 unbonded electrons. And my boron in the middle has 3 electron groups. It's got 3 bonds and no unbonded pairs. Unbonded pairs are often called lone pairs. And the furthest they can get apart is 120 degrees. That is called trigonal planar. So trigonal planar looks like this. And so it's called planar because all 4 atoms, the fluorines at the ends of the toothpicks and the boron in the middle, can all fit in a single plane. They could lie in the sheet of a paper. Now, if I have, imagine I have a model. I don't have an example right in front of me right now, but imagine I have an example where I have 3 electron groups, but one of them is an unbonded pair. So it would be some atom, some central atom with an unbonded pair, and then bonds to 2 atoms. So there's 3 electron groups, but this time it's two bonds and 1 unbonded pair. If I look back at my model here, my crude model, and I take out one of the toothpicks, I could represent the unbonded pair with like push pins. So I still have 3 things that are separating as far apart. 1 bond to an atom, another bond to an atom, and my unbonded pair. So they're still relatively in the same amount of, they're in the same orientation, but now my molecular shape has changed. We're looking for the shape of the molecule. We look at the angle between this atom, the central atom, and the other atom. What is this angle?
120.
It's still 120, but we call this shape bent.
Right.
So this is 120 degrees, and the name of the molecule shape is bent. And I usually like to, because there's 2 different kinds of bent, I want you to be able to specify the angle. Okay. I'm dripping lime juice on myself. Okay, so now there are different kinds of molecular shapes that have 4 electron groups. Ones that have a central atom and 4 bonds.
What was the difference with the 2 different angles for bent? You said there were 2 different angles?
Yeah, you're gonna see it after this.
Oh, it's one with 4 bonds?
Yeah, it's
okay.
yeah. So there's one with, there's different kinds of molecules that have 4 electron groups. They can have 4 bonds and no unbonded pairs. They can have 3 bonds and 1 unbonded pair. And they can have 2 bonds and 2 unbonded pairs. Okay, and the first thing is, the simple case is to look at something that has 4 bonds and try to figure out how far apart that things can get from the central atom. And you might think, in class I would do this, you guys get a chance to do this yourself. Because often what people think is that 90 degrees is the furthest you can get apart. But it turns out that's only using one plane. If you go into the 3rd dimension, you can actually get things that are 109.5 degrees apart. Okay, so and this is a molecular model showing this shape where all of our 4 electron groups are as far apart as they can be, and that angle is 109.5. Now, the name of this, and everything in this group that has 4 electron groups, the electronic shape is tetrahedral. When there are no unbonded pairs, the molecule shape is the same as the electron shape, and so this would be called tetrahedral. And an example of this is methane. Now, if you have 4 electron groups, this is shown here, but I have 1 electron pair, unbonded pair, then you have something that looks like this. So it didn't change the angle between my outer atoms and my central atoms, but I've lost the top of my tetrahedron. So the angle for this is still basically 109 degrees. It's a little bigger because a little smaller because an unbonded pair takes up more space. The name of this is pyramidal. And an example of a pyramidal molecule is ammonia. Where nitrogen is an unbonded pair and then 3 hydrogens coming out. Okay, now if I have 4 electron groups, but 2 of them are to bonds and 2 of them are unbonded pairs, then I have something that looks like this. An example for that is water. Water has 2 unbonded pairs and then 2 bonds to hydrogen. This angle is still 109 degrees, and the name of this shape is bent, but the angle is not 120 here, it's 109. So that's a long answer to your question, Nessa.
Okay, thank you.
Well, Professor,
Yeah?
the text has 109.5 for all of those.
Okay, that is totally fine. Sometimes people care about whether or not sometimes people care about the minor difference. And my only concern is that you know that this, for water, the angle is not 120, it's
Right.
109.
Right,
And the electronic shape is tetrahedral,
right.
and the molecular shape is bent.
So there's really no, to me, there's really no easy way to remember this. Is there any little trick or any little saying or something cute to do this? If you were asked a question on an exam, what type of question, can you give an example of a question that we may get on this particular area?
Oh, I would give you a molecule and tell you to do the Lewis structure and then tell me the electronic and the molecular shape, the name,
Understand.
and
Okay.
yeah. This table hopefully helps summarize everything. And I think, I mean, really linear, that's pretty simple, right?
Right.
Trigonal planar, if you take off one leg of the trigonal planar molecule, you have something that's bent, right?
Yeah.
Right.
And then tetrahedral, if you take off the top leg, you have something that looks like a pyramid. That's why it's called pyramidal.
So you're saying that the electron shape and the geometry shape are two different things?
Electron and molecular.
So this number gives you the electronic shape. The number of
You would
electrons.
draw the molecule the same way for everything, right?
I'm sorry, say that again.
You would draw it all the same way? You're like, it's the molecule still looks one way, we're just describing different things about it?
Yeah.
Okay.
Yeah. So each molecule has an electronic geometry and a molecular geometry. And those names are the same if there's no unbonded pairs. The molecular shape, you have to take into account the electronic shape and the number of unbonded pairs.
Okay.
Okay. So what do you guys want to do next?
Can you go over polarity? Because I didn't understand any of that.
Okay, yeah, polarity is challenging. Okay, so with bonds or molecules?
Like all of it.
Okay, I'll start with bonds and build up.
Okay, thank you.
Oh, and let me give another example of a trigonal. Well, actually, we'll do that later. Okay. Let's say, so polarity. Polarity refers to a separation of charge. Okay, we know that chlorine is a diatomic molecule, right? Cl2. Yeah. And so the electrons in this bond are shared. And because the electrons that are shared are between two chlorines, those chlorines have the same ability to pull the electrons towards the nucleus. So these electrons in the bond are equally shared. So you think about electrons in covalent bonds is there's a tug of war. It's the nucleus of one atom grabbing electrons from the next, and the nucleus of the other atom grabbing electrons from the other, its pair. Mm-hmm. When the two nuclei have the same ability to pull electrons, and that would always be the case between two atoms of the same kind, those electrons are equally shared.
I thought there was a question and it said nitrogen, diatomic nitrogen was polar.
No, that's not true.
Okay.
No, that's not.
Okay.
That's diatomic nitrogen. The two nitrogens will have the same ability. There's a triple bond there, but that will be nonpolar.
Okay.
So, Professor, back to that top one. Between the two, that would be a covalent bond, correct?
Yes. Yes.
Okay.
Okay. Now imagine we have, instead of a bond between chlorine and chlorine, let's say we have a bond between carbon and oxygen. Okay, and we won't pay attention to the rest of what's going on, but we're just focusing on the bond between the carbon and the oxygen. Carbon and oxygen have different abilities to pull electrons from each other, and that's called electronegativity. Electronegativity is a unitless number that describes the ability of an element to attract electron towards itself. Fluorine is the most electronegative element. Cesium is the least. And if you can remember those two things, you can figure out the trends for electronegativity. As you go from left to right, atoms get more electronegative, and as you go from bottom to top, they get more electronegative. So the most electronegative is here, and the least is here. So between carbon and oxygen, oxygen, because it's towards the right, has a greater ability to pull electrons away from carbon. More electronegative than carbon. That means in that tug of war for electrons in this bond, oxygen is going to pull more than its fair share than carbon. And so when it has more electron density around its nucleus, because it's pulling more than the carbon, it's going to have more electrons around it than it would normally, and that will give it a partial, that's a delta sign, it means partial, a partial negative charge. It's not a full negative charge, it's less than 1, but it's greater than 0. And that electron density came from carbon. Carbon lost electron density. It started out with some amount when it was by itself, and then it lost some to the oxygen, and that's now got a partial positive. So we have a separation of charge. And that separation of charge is what results in polarity. So this is a polar bond. And polar bonds have what we call dipole moments. And the dipole moments are represented by vectors with arrows. And I always remember that the tail of the vector, I draw as a positive sign, and it goes with the partial positive. So it goes from positive to negative. So this is a polar bond.
Is there an example of a polar bond or a non-polar bond between, because you said that the non-polar were the diatomic molecules, but are there other molecules that are non-polar?
Yes, I can give you actually a really simple rule of thumb. So for us, the following are non-polar. Bonds between the same kind, of course there's shades of gray, but at this level we can break it up more simply. So bonds between the same element, non-polar. That's one. And then the other major one, and this is really important, is CH bonds are always considered non-polar.
Professor?
Yeah.
They have a table, these negativities on it, so you can calculate these values. Would we have to, you wouldn't ask us a question on that where we'd have to go into a table like that, would you? Fluorine is the worst. Fluorine's, I think it's number 4. Everything's based off of fluorine, correct?
Yeah. And it's funny, it's so fluorine is 4, I think cesium is 0.2 or 0.3.
Right.
So there's 2 types of problems that you would see with this. I might ask you to calculate the difference in electronegativity, and that you use that table for that. So you'd use the electronegativity of one element minus the electronegativity of another element. For that, I would have to give you the numbers. I'd have to give you the table.
Yeah, thank you.
No, you don't have to memorize it.
Thank you.
The other kind of question is this molecule or bond polar?
Right, right.
And for that, you have to use the periodic table and know the trends. And what I would say is anytime you have a bond between two atoms of the same element, it's nonpolar. And whenever you have a CH bond, it's nonpolar. Everything else, there's some amount of polarity.
So
So
like methane would be nonpolar.
yes. So methane, CH4, it has only nonpolar bonds.
Yeah, because something like,
So wait, let me finish. So this molecule is nonpolar.
right, right.
If there are no polar bonds in a molecule, the molecule is nonpolar. Okay, what's your question, Bill?
Like, for example, carbon and sulfur would be nonpolar.
CS?
Carbon and
Uh-huh.
sulfur, yes.
I
That's
would
a
consider that,
nonpolar bond.
this bond is polar.
I mean, but it's, if you look at that delta EN, it's going to
Yeah.
be 2.5 minus 2.5.
Yeah, I would, so if I'm asking you to calculate it, that's one thing, but without it, I would allow you to consider it polar. I'd try to
Okay.
not give you examples that are that close.
Understand?
Yeah, so let me, so this bond, carbon to chloride, that is considered a polar bond.
Right.
And chloride would be the stronger one.
Yeah.
Okay.
So the partial negative charge will be on chlorine, partial positive is on carbon, and the dipole will look like this. Now, if you have carbon tetrachloride, this molecule, now you have chlorine, and remember now, this is a good chance to review. Okay, so I've got carbon tetrachloride. How many electron groups do I have?
4.
There's 4 electron groups, and there's no bonds, I mean, no unbonded pairs, right?
Yeah.
So what is the electronic shape for this,
Tetrahedral.
right? And we got that from this table. I have this. So the electronic shape is tetrahedral, and the molecular shape,
Also tetrahedral.
also tetrahedral, because there are no unbonded pairs. So
Right.
what is this angle?
109.
Yeah, 109.5. Now, this molecule has polar bonds, right? Because I said that the carbon chlorine bond is polar. And so there are dipoles along the directions of each bond. So there are bonds are polar. However, all of those dipoles cancel. So this is a non-polar molecule.
Right.
So anytime you have a central atom with bonds to all of the same element and no unbonded pairs, it will be a nonpolar molecule. I'll write that out because this is important. Anytime a central atom has bonds to all the same element, without an unbonded pair on the central atom, The molecule is non-polar because all the dipoles cancel. The classic example for that is this. It's easier to see here. Okay, so this is CO2. And is the C double bond O, is that a polar bond?
Yeah.
Yeah, right. So there's a partial positive on the carbon, partial negatives on the oxygens. The dipoles run like that, but they are equal and opposite, and so they sum to 0. So CO2 is nonpolar. I have a central atom. It's bound to all the same kind of element, and it has no unbonded pairs. So it has polar bonds, but the molecule is nonpolar. Let me give you an example of a molecule that would be polar. We did PBr3. This was the Lewis structure we had. Okay, so how many electron groups does this have?
4.
4 electron groups. And it's 3 bonds, 1 unbonded pair. Okay, so what is the electronic geometry?
Tetrahedral.
Right, 'cause I got that from the total number of electron groups. The electronic geometry is tetrahedral. What is the molecular geometry?
Pyramidal.
Yeah, it's going to make a pyramid. Say it 5 times to yourself and then you'll remember it. Okay, so now we have so we have tetrahedral geometry and pyramidal. Do we have polar bonds in this molecule?
Yes.
Yeah, because if we look at the periodic table, here's phosphorus, here's bromine. They're not the same. Bromine's more to the right. So we're gonna say that it's partial positive on the phosphorus, partial negative on the bromine. And so there are polar bonds. And actually, I can make a little model. So this is what my PBr3 would look like. And my dipoles are gonna go here, here, and here. But there's nothing opposing up here. Do you guys see that?
Yeah.
It's kind of hard with the slow video. And so because I have this unbonded pair up here, which is this, my dipoles are not going to cancel. So I have polar bonds and this molecule is polar. Hopefully that helps.
So the BR is going to try to strip that electron from the phosphorus, correct, Professor? So the arrow will come down, correct?
Yeah. And of
Okay.
course, I'm afraid to look at the table of electron negativities to see if it bears it out. Bromine's 2.8. Yeah. Phosphorus is 2.1.
Would you give us something that close on the exam? Because I wouldn't like looking at the periodic table. They're very, they seem to cancel each other out.
Oh, because one's over to the right and one's down. I would be forgiving.
Okay.
Yeah, I'll try to do it with things that are, on the exam, I would probably do phosphorus and chlorine, right?
Yeah.
That way it's clear.
Yeah.
Either that or I would, my expectation is that you would call it polar because they are different,
Right.
but I might forgive the direction if there's
Yeah.
a competing concerns. So this is really like the chapter in a nutshell.
Perfect. Thank you.
Taking a molecule, doing the Lewis structure, determining the geometry, and then deciding whether or not it has polar bonds and whether or not it's a polar molecule.
Did you do the Lewis structure for carbon monoxide?
Oh, ick.
Okay, it's not just me then. Good.
Do you want me to?
Yeah.
Okay.
Or at least like lay out a thought process and how you would. Cause
Yeah, I wanted to do, did you see I put up new videos? When did I do that? Yesterday. Did you see nitrate?
no.
I put up a couple, I think I just did one more video. Let me know, is there a topic that you think needs more videos?
The polarity maybe doesn't have any videos.
Okay.
Or it didn't when I
So
last checked.
I couldn't decide if I was overwhelming you guys with too much to look at,
It
or,
helped. No, it wasn't too much. I mean, I went through every one of them.
okay.
It all helps.
Because I'm looking
Yeah.
at my views on
Anything
my
helps.
YouTube channel and I'm not overly excited about how many views I'm getting. Okay.
Look at the CO. You know that's going to be a polar bond there already out of the box, don't you?
You do. Yeah.
Yeah,
it has
but that
to be
doesn't
polar
help with
bond.
like if it's a double or a triple.
Yeah. So that's a good point. So Bill looked at that and said, oh, this has to be a polar molecule, right? Because I don't have a central atom. And I have something that's going to be unequally shared, whether it's 2 or 3. Okay, so there's 4 electrons from carbon and then 6 from oxygen. That gives us 10. It's carbon and oxygen. I'm going to put in 1 bond. That takes away 2 electrons. That gives me 8 left. I don't have an outer or an inner, so because I only have 2. How would I do this? Oxygen's more electronegative, so I'm going to fill its octet first. That takes away 6. I have 2 left. But now carbon only has 4 electrons, so I'll take that, put that there. 2, 4, 6, still not enough. I think you have to do the triple. 2, 4, 6, 8. 2, 4, 6, 8. Yeah.
It'll work.
And that would be polar because there'll be a partial positive here and a partial negative there. Polar bond and polar molecule.
So you just start by putting 1 bond and then subtracting and filling the octets and then just sharing them until they each have an octet.
Yeah.
Those are
And I
the
always do and you know what? I actually learned Lewis structure is a completely different way. This method, in my years of teaching it, and I've been probably teaching it this way for, oh my goodness, I don't know, a lot of years, at least 10. It's never failed me.
okay.
Sometimes if I go out of order, I might come into a problem, or if I skip a step, but it always works.
Could you do an example of a molecule with 3 different elements, like ammonium hydroxide or something?
That's complicated in terms of polarity.
No, in terms of the Lewis structure, because I was having difficulty choosing where to bond them.
Oh, okay. So, well, ammonium hydroxide, let's see.
You don't need to do that. I was just
Yeah.
one with.
Before you leave that top one, the C carbon monoxide.
Yeah. What was the
And look
question?
at this. Right
Uh-huh.
now, you have 8 for carbon.
Yeah.
And you have
8 for oxygen.
Right. Now, if you were to do the formal
Yeah, I didn't do that.
for that,
It's probably not.
Okay, it's going to look a little weird.
Yeah, carbon would be 4 minus 3 minus 2, right? That gives me minus 1.
Yes.
And the formal charge for oxygen would be 6 minus 3 minus 2. That gives me plus 1.
Oh, okay.
Well, so you could make an argument that this is not so good because carbon has a negative formal charge and it's less electronegative.
Right.
So what else could I do?
That triple bond is what's got me kind of flustered in there for this particular problem you just did with that carbon monoxide.
I would say don't, I think this one is going to be, this is pretty complicated.
Understand?
Yeah, and then for the ammonium hydroxide,
Okay.
on something complicated like this, I would give you a skeleton. So let's say,
Good.
they usually told you what was on the inside. So there's formamide, no, formaldehyde. Formaldehyde is CH2O. But I would give you, I think I would tell you carbon is the central atom.
But
Okay,
then
that helps.
oxygen is like bonded to the hydrogen, not to the carbon.
No, it's bonded to the carbon.
Because I saw one where there was like a central atom, but then there was an atom bonded to another atom that was bonded to the central atom.
Yeah, I wouldn't do that on a test unless I gave you the skeleton.
Okay.
I would arrange the atoms for you.
Okay.
Some things to know. I did put a slide in the PowerPoint. Oxygen can have 2 bonds. So that's the problem with this. Oxygen can't have 3 bonds.
Right.
So how would that be? If I did that, it would have to be like this. Yeah, I don't know. Don't worry about that.
Yes.
I'll look
That
at it later. It's gonna bother me now. Oxygen can have 2 bonds, and when oxygen is like this, or like this, it has a formal charge equal to 0. If oxygen looks like this, it has a formal charge equal to -1. Carbon can have 4 bonds. It pretty much always has 4 bonds. Hydrogen can only have 1 bond. So that means it's always going to be an outer atom. Always has to be on the outside. Nitrogen is either going to be an unbonded pair with 3 bonds. That's a formal charge of 0. Or nitrogen can have 4 bonds, and then it has a +1 formal charge. There's a slide in the PowerPoint with that.
You know, Professor, I think on one of your on your lecture series, you had about 4 or 5 of these to do, and I think, if I'm not mistaken, you said pick it out and figure out what was wrong with it. Did you do you remember that?
In the lecture with electron configurations, or
Yeah.
with
Pearson, there was something like that where you had to like fix the Lewis structures.
Right, fix the Lewis structure. Well, one of them, it was not symmetric. Oxygen was sitting over here on the top to the left, and on the bottom it was sitting to the right. It wasn't symmetric around that central atom. And I looked at that thing. I said, I could never get this on my own.
Oh, well, let's do, they're not always going to be symmetric. Let's do carbonate,
Okay.
because we haven't done resonance structures. So first of all, carbonate, that's a polyatomic ion. So this is going to be polar because it's ionic.
Right.
Anytime it has, you have like ammonium, nitrate, any of the polyatomic ions, it's going to be polar. Okay. So number of electrons is going to be 4 for the carbon, plus 6 times 3 for the oxygen. And then we have to add 2 because of the charge. That negative charge on the carbonate comes from 2 additional electrons from the valence ones. So that gives us a total of 24 electrons. I'm going to put carbon in the middle, oxygen, oxygen on the outsides. I'm going to do this in pencil. And then the next thing to do is to add bonds. And 2, 4, I have 6. So that gives me 18 left. Then I'm going to fill the outer octets. You'll learn your 6 times tables really fast. Okay, so 6 times 3 is 18. So I've run out of electrons. So what is wrong with this structure?
Carbon only has 6.
Yeah, carbon does not have an octet. So what I'm going to do is I'm going to borrow from one of the oxygens. Now I could borrow from any of these 3 oxygens. It doesn't matter which one I take from. So maybe I'll do this one first. Okay, so now if I look at my formal charges, I have an oxygen with 2 bonds and 2 unbonded pairs. And I just said that those will always have a formal charge of 0. So it's 6 valence minus the 2 bonds minus the number of unbonded electrons, that's 0. These oxygens, those have a formal charge of -1. My carbon has a formal charge of 4 minus 4 and no unbonded pair, so that's 0. So I have -1, -1, 0, and 0. That's okay, because I have to have a -2 total formal charge. Okay, but now, this is not the best complete representation of this structure. If you look at, they can actually do crystal structures. It shows that the carbon-oxygen bonds in carbonate are all the same. And actually, they are shorter in length than a carbon-oxygen single bond. And a carbon-oxygen double bond is shorter than a carbon-oxygen single bond. The carbon-oxygen bonds in carbonate are consistent with being shorter than the single bond and longer than the double bond, and they're all the same. So what that means is that sometimes the double bond is here, sometimes the double bond is here, sometimes the double bond is here. And the way we represent that is to draw all possible structures. And those are called resonance structures. So the best way to represent carbonate would be like this. So whenever you have some point where you have to choose where to put a double bond, and it could go to any of more than one of the same kind of atom, that's suggesting that you're going to need to draw resonance structures later. And so these are the resonance structures. We represent them with double-headed arrows, and we just move the double bond to where they should be, where they could be. So incidentally, what is the shape of carbonate?
Trigonal planar.
Yeah, there's 3 electron groups, and there's no central unbonded electrons. So this is trigonal planar, and that is the electronic shape, and it's the molecular shape. And this is polar because it's an ion.
Right. Now, Professor,
Yeah.
on this right there, don't they have a composite one where they have double bonds for all 3, and they put the brackets around it and put 2 minus?
The only thing I've seen is something
They had it drawn in the book, I think. They
like
put the
this.
brackets there. Yeah, they had something like that, yes.
Yeah. That's hard. I've seen that represented more when you have two, not so
Mhm.
much when you have three.
Okay.
But so this is a single bond, right? This is a double bond. The order that we expect for this is actually 1 1/3 bond order. I don't think they go over that in this book.
Yeah.
Because that double bond is shared among three, so it gives a third to each of the singles.
Mm-hmm. I have a question for you. I
Uh-huh.
think I remember this one problem. Can you have like on that central element? Can you have two central elements with the hydrogen and oxygen? Like for example, the one I got hung up on, you had two nitrogens in the middle, and you had the two
Oh,
hydrogens side,
into
and then you had an oxygen at the top and
this
another
one,
oxygen at the bottom coming off the nitrogens.
right?
Yeah, and draw H to that side, and then coming up off that straight off that nitrogen, you had an oxygen.
Oxygen?
Yes, I think it was oxygen, and then coming down, it was one H, not two H's. It was one H coming off the nitrogen on either side of it, and then off of one nitrogen, you had an oxygen at the top, and off the other nitrogen, you had an oxygen on the bottom. So you had two nitrogens in the middle,
Uh-huh. Say it again.
and straight up on one, you had an oxygen,
Okay.
and on the other one, coming down, you had the oxygen.
On this one.
On the other nitrogen, yes. And then you had hydrogens on either end of the nitrogens.
Like that?
No, just straight across.
But
Yeah, it could be that way. Yeah, that kind of thing. That thing threw me off big time.
okay.
There it is.
So let's add up the number of electrons. There's two H's, right? Each have 2 electrons. There's 2 nitrogens, they each have 5. And there's 2 oxygens and they each have 6. So this has a total of 24 electrons. So here's where certain rules of thumb will make it easier. Oxygen should have 2 bonds if it's not charged. Nitrogen should have 3 bonds if it's not charged.
Okay.
So I have 24 electrons. With the bonds, I've used 2, 4, 6, 8, 10, right?
Right.
I have 14 left. The hydrogens are done because they can only have 1 bond.
Mm-hmm.
24, do I have that right? What would I do? This is a weird structure. It was nitrogen in the middle, not carbon?
Yeah, I forget which one it was.
Oh, I think
there were 5 examples, and they had this one. My problem was I had a tough time just trying to draw the structure. I didn't have a clue on how to draw that, you know.
The framework?
The framework, I didn't know what to do.
I'll give you a complicated framework. I don't think this is a molecule.
Okay, it could not be, but
Okay. Okay, so give the homework a shot. I saw that that 2 of you started it and finished it. It doesn't look like anybody else started it. So give it a shot. Hopefully the lecture will help. I'll post this on Zoom. I think we've covered everything I wanted to cover. Do you guys have any other questions?
No, that was it for me.
Okay.
Too, Professor.
Yeah, thank you, Professor.
Okay, I'm gonna stop there. As always, email me questions, and you know what I was gonna suggest? Canvas is so hard to email with pictures. If you're doing, especially with Lewis structures, if you are doing Lewis structures or bond polarity and stuff like that, you guys have my Gmail email address. Don't use Canvas. Just on your phone, take a picture of what you're doing and send me the picture of your problem directly to Gmail, because Canvas strips it. So that's the easiest way to get a quick answer. Is it okay?
Yes.
Yes.
Okay, thank you, Professor.
Yeah, I didn't even realize that Canvas makes me log into Canvas and makes you guys log into Canvas to attach a photo. That's the easiest way to get questions on especially this stuff. Okay. Well, good luck, you guys. You everyone who's still in is doing well.
Bye-bye.
Bye.
Thank you, Professor.
Thank you.
Thank you, Professor. Bye.
Nice hearing
Bye.
from you guys. There we go.